Okay, so we talk about configuration requirements. When you're talking of configuration, you simply mean the setup. Okay, so how the the building is actually uh, made in such a way as to deal with the earthquake resistance uh, behavior or concept. So configuration requirements will allow us to be guided accordingly with how your building will be responding better to seismic forces. And for this lecture, I will be discussing to you the importance of regularity and irregularity in structures. Okay, so we have two types of structures. Uh, Basically, we have the regular type and the irregular type. Okay, so the definition of which are based on the subsections of this code on configuration requirements. So for regular structures, the definition is such that these uh, have no significant physical discontinuities in plan or vertical configuration. Okay, so we have two considerations again when we talk of regularity and irregularity. So we have the plan and the vertical setup. Okay, so when you say plan, this can be termed as the horizontal setup, and this is the vertical setup. Okay, so you have to check on the regularity and irregularity based on the horizontal or the plan and the vertical configuration of the building. So for irregular structures, the definition is quite broad in the sense that we have to deal with table 208-9 and table 208-10. Okay, so for regular structures, all you have to take note of is that there are no physical discontinuities. Okay, so discontinuities simply means there's no point wherein the transfer of stresses might be affected. No, when something is not continuous, then there is weakness. Okay, so discontinuity will create weakness to your structure. So if there is any physical discontinuity, then the structure will be irregular. And for the irregularity consideration, we have to find out what particular irregularity is manifested in the setup or configuration of your structure. Okay, for number one, the physical discontinuities are actually based on what you call the LFRS. Okay, so this is the lateral force resisting system. So I'd like to show you a figure here first before we proceed with that. So this is typically a building frame which is shown in a vertical setup. Okay, and notice there's some discontinuities. Obviously, if you look at in the visual aspect of it, the discontinuity is actually focused on this part here, okay? And where are the elements that produces the configuration or setup of your building? Okay, so we have the lateral force resisting system. So these are now the LFRS. Okay, so all these columns here contributes to your LFRS. Okay, so each and every column will help your building withstand the forces of earthquake. Okay, so these are all part of the lateral force resisting system. If there's a shear wall added inside or maybe at the side of the structure, then your LFRS can be composed of columns and shear walls. Okay. Sometimes for very sophisticated structures, you also have what you call the braces, no? So it can also be a part of the LFRS. So this brace here can be a part of your lateral force resisting system. Okay, and so on and so forth. So there are a lot of elements that you can add into the LFRS, but basically we have to bear in mind that for simple structures, we only have the columns and the shear walls to contribute to the resistance of your frame directly uh, against the forces of earthquake. So another element that is normally made into the configuration is the diaphragm. Okay, so a diaphragm is actually a horizontal a member which is typically a beam or a slab or a beam slab uh, system. So you call this now your diaphragm. So a diaphragm is very essential since it is the one that's holding your LFRS together. Okay, so if there's no diaphragm action, the LFRS will not behave in harmony to resist earthquake forces. Okay, so all the beams, all the lateral force, or the horizontal members are part of your diaphragm. Sometimes a portion of your lateral brace can be helping, no, the action of the diaphragm to transfer the loads from one column to the other, but basically the main purpose of a cross bracing is to add to the strength of your LFRS system. So mainly the diaphragm is made by slabs and beams. Okay. Uh, when we're talking of other elements in the configuration of your building, we only have to consider, of course, those elements which are major part of the building. So other elements which are non-structural in nature can be neglected. So there's a note here that all occupancy in categories 4 and 5 need to be evaluated only for vertical irregularity 5 and plan irregularity 1. Okay, so but I forgot to add it here that this is only for zone 2 requirement. That's why when we are talking about the Philippine setting, all occupancies including 4 and 5 are not exempted to be considered in your uh, configuration for irregular structures. Okay, so by the way, 4 and 5 are the standard occupancy, and this the miscellaneous occupancy. Okay, so okay, so you have to memorize now the categories 1 to 5 in the order of importance or significance. Okay, so the first one is, I think, essential. Okay, essential, then hazardous, then special, then standard, then miscellaneous. Okay, so if we are talking about the hierarchy of categories, the most significant or the most important are essential structures. From the word in itself, they are essentially uh, built for a purpose. So they must resist earthquake because they are the ones that are needed in case of disasters. So for number 2, hazardous, of course, it is also important because it will add up to the problem when hazardous facilities are damaged. And for special, there is a, a freedom to categorize which are special structures and which are not. So depending upon how you look into the code, and of course the more common is the standard and the miscellaneous, because this is the day-to-day structures that we see outside the malls, the houses, the apartments, the commercial establishments, the things that we ordinarily see in our day-to-day activity. Okay, for number 2 definition of irregular structures, we have to bear in mind, by the way, 2 and 3, we have to bear in mind that we have to look at the two tables here. No? In order to define what irregular structure is, we must have some understanding on what the table 208-9 and 208-10 offers us. And I actually summarized this table in the form of an enumerated list here of vertical and plane irregularity. Okay, for vertical irregularity, we have 5 no, irregularities. Okay, the first one is what you call the stiffness irregularity. By the way, before I proceed, I'd like to explain to you the meaning of what adjacent and above and below means. Okay, so when we are pointing on a reference story, let's say this 1 to 3rd story here, or 3rd level. Okay, the adjacent stories are the 2 stories above and below. Okay, so this story and this story are called the adjacent story. Okay, so adjacent means it can be on top or it can be at the bottom. It can be above or it can be below. So basically, the vertical irregularity uses the word adjacent and separates it from a specific description on above and below. Okay, so take note of that. Okay, for stiffness irregularity, or what you call soft story, so softness and stiffness are actually the variables which are related here. So we have to compute for K of the story, okay, in question. So when you're computing K, you're just like computing R in our, or the rigidity R. So remember our computation last time about rigidity, which is basically 12 EI over L cubed for columns and shear walls. Okay, so this is applicable for columns and shear walls. So if the K of the story is less than 70% of the K of the story above, okay, so this is specifically above, then you have a soft story. So that's the meaning of this. You have to check each condition. So if it passes here, pag pumasa siya dito, you check the second. If the K of the story is less than 80% of the average of the K of the 3-story above, of course, if there's no more story above, that's not applicable. Okay? So you have to bear in mind that this is a general statement that we have to apply on each and every situation. So we have to use our judgment in case there are confusions or gray areas which are existing in the problem to be solved. Okay, so soft story or stiffness irregularity are just referring to your rigidity of your columns here. Okay, we're talking of the total column on the story, not individual columns. Okay, for weight mass irregularity, you just refer to the section that is cited here in the lecture. The mass of the story must be always less than 1.5 of the mass of each adjacent story. So when you say adjacent, you are checking it on the story above and below. Okay, so that's the difference between a specific term here above and a term which is known as the adjacent. Of course, there's a note here that if it is a roof, you don't consider it as an irregularity because roofs are very light compared to floors. Okay, so if you have a roof which is made up of GI sheets, you might say that it's a soft story. No, okay, you don't have to consider roof because roof only serves the function of guarding against rain, sunlight, without any permanent loads that might damage. Of course, winds are transient loads that can cause damage, but it has nothing to do with earthquake uh, earthquake effect. Okay, so pag nilindol ka at bumagyo, you call it really a disaster. Pag nagsabay pa yon, okay? So, hindi naman siguro. Huwag naman sigurong dapat mangyari yun. Okay, for vertical geometric irregularity, we now talk of the elevation or the vertical plan or the vertical setup configurations. So we are talking here of edge or the height. Okay, when you talk of the height, you're talking of the height of the LFRS, or simply the height of the column or shear wall. Okay, so the height of the column or shear wall in a story must be always greater, sorry, must not be greater than 1.30 times the height of the LFRS in the adjacent story. So what does that mean? If I have a 4-meter height of a story, the adjacent story must not exceed 30% of this. Okay, so if I multiply 30%, my limitation for the story above and below must only be 5.2. Okay, if I exceed this, can I exceed this value? Yes, you can, but you have to tag it as a vertical geometric irregularity. What the code says is that if you don't want to be adding burden to your computation and analysis, you just stick to the code, because the code primarily collected some information about restricting your uh, restricting your height changes uh, greater than 130%. Of course, if you want to make your own study out of it, uh, you have to prove, okay, that your procedural analysis is well substantiated and on facts. But if you don't want life to be difficult, you just follow the law. And the National Structural Code of the Philippines is a law that serves as guidance for each and every structural engineer to follow. Okay. So note that the LFRS lateral force resisting system does not mean penthouse as a part of your uh, story. Okay, so those penthouse should not be considered, because sometimes penthouses are normally made on top of the roof, placed on top of your roof deck, and then the height must always be um, differently uh, designed as far as the building's height or story height are concerned. Again, the reason for that is because it's just considered not a major part of the lateral force resisting system. But of course, we are talking of earthquake here. If we are talking of wind load, it's a different scenario, no? It might not be a concern in earthquake engineering, but it is a concern in wind engineering, because you are placing a structure on top of your building. So for number 4, in-plane discontinuity in lateral force resisting element irregularity. Okay, so the word in-plane discontinuity and out of plane, you have two types of discontinuities here. But for vertical, we are more on the in-plane discontinuity. So the in-plane discontinuity can be visualized in this, okay, in this figure here, wherein if you look at the columns, they are all straight from top to bottom, okay? While at this portion here, there's a discontinuity. When you say discontinuity, the column was cut here and moved here, okay? So this is now an in-plane discontinuity. Okay, remember that all the columns here must be a part of frame B. Okay, so meaning to say that when I cut the section here, let's say I actually get that section from this plan. So if I cut a section, so that's frame B here. Okay, so if I cut the section, the column that I'm actually referring to is this column. So it must be a part of this frame, starting from your module B here up to the end. Okay, so this column here, which is out of plane, is not a part of the frame B. Okay, so don't consider this. So you only consider an in-plane discontinuity when it falls within the plane that you are actually uh, analyzing. Okay, but if you can avoid this, it is much more practical to avoid it. Okay, the in-plane offset of LFRS must not be greater than the length of the LFRS. Okay, I'd like to remember you class that these conditions that I set forth here in my lecture simply states that if this is satisfied, then you have an irregularity. If it is not satisfied, then you are safe. Okay? So let's move to the last discontinuity on the vertical irregularity, which is the capacity irregularity, or what you call the weak story. Okay, when you're talking of stiffness, you are talking of soft story. Okay, so when the word stiffness, the word stiffness is synonymous, not synonymous, but analogous to the word soft. Okay, so your story can be stiff or less stiff, more stiff, less stiff, soft, hard. Okay, when you're talking of capacity, you are talking about the strength of your uh, setup or your building configuration. Okay, it can be strong or weak. Okay, so if the story is soft and the story is weak, then you have an irregularity in stiffness and in capacity. So they are different, no? So this is category number, I think, number 1 in our vertical irregularity, and this is number 5. Okay, and the computation is such that your strength of the story or capacity must not be less than 0.80 of the strength of the story above. Okay, not adjacent, but above. So which means that whenever you go from lower story to upper story, your strength must be maybe decreasing, but not, of course, very significant. Okay, so you cannot have a stronger story on top and then a weaker story at the bottom. That's a no-no to configuration requirements. So let's move over to the plan irregularity. We also have, I think, 5 of this. So for the first one, the torsional irregularity are considered when the diaphragms are not flexible. By the way, I forgot to I think this is spelled misspelled. So this is Diaphragm. Okay. So I forgot to tell you a while ago that aside from having a slab system, we have to take note that diaphragms here are maybe flexible and rigid. Okay. So how do you say that your diaphragm is flexible or rigid? So this is the consideration. So the consideration for flexibility and rigidity is measured in terms of torsion. So that's why this is called a torsional irregularity, and it is actually checked simply by computing the the deflection or the story drift at one end and the story drift at two ends. Okay, so if you have basically two buildings here, okay, so this is the earthquake is the moving back and forth like this. So the ends that you are referring to are these two ends here. Because this end and this end here will just move the same if this is rigid, okay? You don't have to check it here and there because this will move just the same with this, okay? So if I have a node here, 1, 2, 3, 4, one will just move in this direction, the same, more or less the same nature as that 3 will move in this same direction as 4, okay? So you have to check delta 2 and delta 4. So delta 2, if I change this, delta 2 must not be greater than 1.20 of the average of delta 1, delta 2 plus delta 4 divided by, okay, take the average, you divide it by 2. So if this is satisfied, then you have a torsional irregularity. If this is not satisfied, then you don't have a torsional irregularity. So that's how you configure your setup. No, you're just like diagnosing a person which is seeking your help. Okay, so you can diagnose it on these aspects. So number 2, we're talking of re-entrant corner. So before we proceed, what is a re-entrant corner? So a re-entrant corner is actually an interior corner. Anything that you see on the interior aspect of the plan. Say I have here a building which is like this. So what is my interior corner here? My interior corner is actually this one. So I have a re-entrant. You call this now a re-entrant corner. So a building can have as many re-entrant corners as it can, depending upon the design. And the National Structural Code of the Philippines and other codes do not want buildings to be having a lot of re-entrant corners. So there is a saying that the simplest building is the safest building in terms of earthquake. When you build a building that is simple, symmetric, no discontinuity, then that is the most durable building in terms of earthquake. Okay, also a saying that goes simplicity is beauty, so you might as well consider that in earthquake engineering. Okay, so not all sophisticated things are the ones that are aesthetic, no? So you can make it as simple as you want, but the beauty of it can actually shine, not only in terms of aesthetics, but also in terms of strength and durability, especially when you're considering the safety aspect of your structure. Okay, so these are re-entrant corners. So you just look at the projection beyond the re-entrant corner. So what is the projection? If you are talking of earthquake in this direction, my projection is actually this one. This is the projection in this direction. So this distance has something to do with a comparison on the plan dimension in that direction. So it must not be greater than 15% of the plan dimension. What's the plan dimension? If this is letter D and this is your X, so X must not be greater than 15% of D, or else you will have a re-entrant irregularity. So that's the how to diagnose this. It's easy to diagnose it. In fact, if you will look into a lot of buildings here that are existing, you might as well think that a lot of us are violating this. Okay? even especially in places where there's no strict implementation of the code requirements. Okay, so you look at your own home, your own house, your own school, your own the buildings in your neighborhood. Okay, you might as well try to observe. Kaya lang, wag mo na pakialaman, nakatayo na yun. Okay, so little by little you will appreciate things when nalalaman mo lang naman yung importance niyan pag nangyari na yung problem, di ba? So you look into this as graduating students. You must be very observant in this uh, part of your learning. So it's not only all about understanding the difficult calculations, but also these simple guidelines that will help us or help you improve, okay, the analysis and design of structures. Okay, so for number 3, diaphragm discontinuity irregularity, again, we go back to diaphragm, but these are all plane irregularities. So what is a diaphragm discontinuity? I told you that discontinuity means there's a cut, there's a break, no, in terms of the elements that are concerned. Like this, the elements concerned is the diaphragm. So, bakit ka nagpuputol ng diaphragm? Sometimes you cut it out because you want to have an access, like stairwells. You don't want to have an access view. You make a lobby, an atrium. Okay, so you see malls. Nakita niyo yung mall sa gitna niya, butas. From the 5th floor or 4th floor, you can see the ground floor. Of course, those violated the irregularity, but it doesn't mean that you cannot violate it. The meaning of this is that when these are violated, you better go to your structural code and look what is there to guide you perform a good and a safe analysis and design. Okay, so the cutout areas are those which are normally placed on mall atriums, no? So yung mga overlooking lobby ng mga malls. So the diaphragm cutout area, say this is you have here a mall, and then you want to have a lobby here so that you can see the view on the bottom floors or the floors below. So you call this a cutout area. Okay, so this cutout area must actually not be greater than 50% of the enclosed diaphragm areas. What is the enclosed diaphragm area? The enclosed diaphragm area, it must be this total area, considering or not considering the cutout. Okay, so my total area is this one. Okay, so if my diaphragm cutout area is 1000 square meter, or it's too big, let's say 500 square meter, then we have to see to it that 50% of the total, let's say 1000 square meter, should not be exceeded, or else you are violating the diaphragm irregularity. Okay, so for number 4, I already explained to you this out of plane offset a while ago. So if we have the in plane offset irregularity, this is now the out of plane offset irregularity. Okay, So when we're considering frame B, so the out of plane offset is this one. This column here is out of plane by 0.5 meters. Okay, so this is what you call out of plane. Okay, so this is what you call the in plane. In terms of frame B, what if I look at it in terms of frame 3? So if I look at frame 3, it's the other way around. My out of plane offset is this column, and my in plane offset is this column. So you have to bear in mind that what you see depends upon your position. Okay, so when you look into the road and the other side of the road is opposite to you, the other man standing on the other side will tell you that the opposite of the road is actually on your side. Okay, so if you look at frame B, my OOP is this column here. But if I look at frame 3, my OOP is this column here. Okay, so you have to uh, look into those important consideration when you are dealing with these irregularities. So non-parallel system irregularity are measured when your vertical LFRS elements are not parallel to or symmetric about the major orthogonal axis. Okay? So when does this non-parallel system irregularity happens? Usually on the lat area, wherein the lat area is not, let's say your lat area is not orthogonal or 90 degrees. Okay, so my lat is something like this, and then I was asked to build a building here. Of course, the owner wants me to use all the area that I can use. So this part here is actually non-parallel. No? So this and this are non-parallel. Okay, so there are a lot of ways on how to deal with this that you will not violate this, but I will not explain to you now because this is not a part of the lecture. But in case you want to place your columns here, then you are in trouble. Okay, so you place your columns here in a non-parallel manner compared to these columns here. Then these are actually again a violation of your plan irregularity. Okay, if the shaking is in this direction, there will be no major problem. But if the shaking is in this direction, these columns here will behave differently because of torsional effects. Okay, so there's a good way on how to deal with this, but it's a matter of basic theory on center of rigidity computation. Of course, experience will tell a lot here on how to solve this problem. But this is very easy to solve. Okay, so that finishes my lecture now on this irregularity uh, aspects of your building configuration. So if you have questions, let me know, and I'll continue the lecture by giving you an example in the next video.